Hello class, welcome to the another video lecture based on the chapter vapor and combined power cycle. Today we are going to talk about the ideal reheat Rankine cycle. In the previous video lecture we talked about that what are the modification we can bring in the Rankine cycle to increase the efficiency. One of the challenge in the Rankine cycle was the working fluid in the turbine. So basically in the working fluid, if you notice that in Rankine cycle we had a boiler, and that from that boiler the vapor is coming, right? And that vapor is basically going through or expanding through a turbine. However, that turbine exit also contains some moisture, and that moisture is not desirable because that moisture eventually deteriorates the turbine blade, right? So what are the conditions or what are the things that we can improve to avoid that situation, as well as what are the steps we can take to increase the cycle efficiency, right? So one of the thing we could do is that reheating this Rankine cycle. Let's take a look what is the reheat means. Okay, so there is two possibilities that, as we mentioned that we increase the efficiency. There is two possibilities. One is that we need to increase this temperature, right? Turbine inlet temperature. So then if we increase the T3, then we can increase the cycle efficiency, and we saw that in previous class. However, we cannot increase T3 at a point sufficiently high or extremely high temperature that will deteriorate the turbine blade. We cannot do that. So what can we do that then, right? So the first thing, to increase the efficiency, thermal efficiency, number one, we can do that, increase the superheating temperature. However, this is not desirable. Why? It's because it it is pretty unsafe for the turbine blade, right? So another thing we could do for this particular case is that the expand the steam in two stages, right? Basically, use a reheater system. What is that? So first you have two turbine, right? Basically turbine 1 and turbine 2. Turbine 1 is the high pressure turbine and turbine 2 is the low pressure turbine. So taking some sort of output in a reheater, and then basically that reheater that vapor will gain some sort of energy again, or increase the temperature again, right? Cool. So the T3 is always high, and then T4 is decreasing. It's because of expansion, and then that T4 working fluid is coming through a boiler, basically again gaining some heat and increasing the temperature. T5 again it's increasing, and then again it's coming through a low pressure turbine. So now we can see that T3 and T5 right here, it's basically the average temperature is increasing of that cycle. So if the average temperature increase, meaning that cycle efficiency also increase. So that's the reheating process, right? So basically reheat, using a reheater we can increase the efficiency of the Rankine cycle, right? Using a reheater, which will eventually increase the T average uh, of that cycle. T average increased, right? So that's the possible way to increase the efficiency of a Rankine cycle. So now let's take a look on the what is happening on the the Q in Q out or turbine work. Basically when we use two-stage turbine, basically we have high pressure turbine and low pressure turbine. Okay, so we have the TS diagram already here, and we know that as always the Q in is basically right here, right? And also 4 to 5 is this one. Here is also some sort of Q in is happening, which is we named it reheating, and the heat rejection is still same, or the Q out 6 to 1, condenser 6 to 1, right? And this is the work produced 3 to 4 and 5 to 6. and the work consumption or the pump work is basically from 1 to 2. So let's take a look what is happening in the Q in, right? So basically in this cycle, the Q in equals to Q, we call this one is a primary, right? From 2 to 3, 2 to 3, this one is the primary heating, plus the heat of the heat transfer in the reheater, or the Q equals Q of reheat, right? So that's the total heat. So the Q primary is nothing but H3 minus H2 plus, and the reheater is H4 minus H5. Excuse me, the reheater is basically H5 minus H4. So that's the Q in, total Q in of that system. Now what is the W turbine, right? Or the what is the turbine output? Because we have two turbine, low pressure turbine and high pressure turbine. So W turbine of high pressure and W turbine of low pressure. Okay, so for high pressure we know that it's H3 minus H4, because right here H3 is the maximum temperature and then temperature is decreasing, H4. And then for low pressure turbine, the input is 5 and output is 6, so H5 minus H6. So now we know that the W turbine output and Q in, we should be able to determine the efficiency expression, and the condenser and pump, it will be similar to the the Rankine cycle in the previous lecture we talked about. Okay, so that's the expression or the heat heat input and the work output of this modified Rankine cycle. Modified means that basically we are using a reheater. Okay, so remember guys, one very important thing is that this reheater doesn't mean that this this output of the turbine is mixing within the boiler. No, it's not mixing. There is a duct, and that fluid or that gas or the vapor is basically flowing through that duct. So it's not mixing with the water within the boiler. So it's basically it's a too close system, so it's just gaining the heat or gaining increasing the temperature of that working fluid. So that's what is happening. Do not mix with water, okay? Then it will change the entire scenario. Okay, so let's go ahead and take a look to another topic, basically that ideal regenerative Rankine cycle. So we saw the Rankine cycle in Brayton cycle, or regenerative system in the Brayton cycle. So let's take a look on the Rankine cycle, what is happening in the Rankine cycle. Okay, so in the Rankine cycle, regeneration can be done in two ways. One is that open feed water system, another is closed feed water system, right? So this one is open feed water system. What is the meaning of open feed water system? What open feed water system is nothing but we are taking the turbine output, right, in two different ways. One is that it's coming through a condenser, just like the simple Rankine cycle, coming through a condenser, condense it, and it's pumping again. Another, we are taking some part of that expanded gas, right, or expanded vapor through a mixing chamber, right? So basically it's a mixing chamber, meaning that the water and this vapor, right, this is vapor and this is water, they're mixing together right here. So basically if you have, like, let's say 1 kilogram of water vapor is coming, then the y amount of vapor is coming through this way, and the rest of the 1 minus y or y amount of vapor is coming through this way. So basically again it will be 1 kilogram of water, right? So they're mixing together right here. So now the feed water, it's nothing but we call it open feed water system. Feed water system is that the water in the pump, right? Basically the water is feeding to the pump, it's called the feed water. So since the water and vapor is mixing in this chamber, so that's why we called it open feed water system. So the TS diagram of that open feed water system is already given here. So basically 1 to 2, it's simply Rankine cycle, just like simple Rankine cycle. It's increasing the pressure. And then 2 to 3, what is happening here, 2 to 3, it's it's mixing within this open feed water system, feed water heating system. So basically that open feed water heating system, the temperature is increasing and it's becoming saturated, right? Because that vapor is coming as well as the water is mixing, so it's becoming saturated liquid. So right here, 0.3. Again, once the temperature is increasing of that open feed water system working fluid, basically the water, saturated water or saturated liquid, then from when it's passing through the 3 to 4, it's also increasing the pressure again, or the temperature again. So we can see that 3 to 4 temperature and pressure is increasing. And then from 4 to 5, which is the heat addition process, Q in. So basically 4 to 5 here, the Q in, the heat addition is happening, right? So that again from that boiler output, basically it's going to the boiler output, basically it's going to the turbine, and turbine is expanding. Now interesting thing is that in the turbine, 1 kilogram of, just for example, okay, 1 kilogram of vapor, when it's coming through the turbine, there is two outlet. One is that y kilogram of the vapor is coming to the open feed water heating system. Another rest of the amount, 1 minus y kilogram of water, is coming to the pump, right? So that's what is happening. 6 to 7 right here. 7 to 1 is basically this y 1 minus y amount of vapor, right? It's basically condensing. So that's the TS diagram of this modified Rankine cycle. Basically modified means that regenerative Rankine cycle. So let's take a look at the Q in. What is happening in the Q in? Where is the Q in is happening? Right here, 4 to 5, right? So the Q in equals to H5 minus H4. And then Q out, where is Q out is happening? Q out is happening right here, the condenser as well as the open feed water heater, right? So basically that Q out, actually the Q out right now is happening in the condenser with what amount of vapor? 1 minus y. So it will be 1 minus y times H7 minus H1. Okay, so this is Q1, Q out. Now what is the turbine output, right? So the turbine output, we can see that there's two different outlets, so we have to consider these two different outlets. So basically if we simply consider the Rankine cycle, simple Rankine cycle, then it will be H5 minus excuse me, H5 minus H6. However, we have like 1 minus y amount of gas is coming, which is also H6 minus, excuse me, H6 minus H7, right? H6 minus H7. So it will be H5 minus H6 plus 1 minus y of H6 minus H7. And then W pump in, we have two different pump, okay? Right here you can see that two pump 1 and pump 2. So the pump 1 is handling basically 1 minus y amount of water, and then W pump this is pump 1, okay, W pump 1, and then 1 minus, basically the pump 2 is handling 1 kilogram of water, right? So we don't have to write 1, instead of I'm just writing pump 2, okay. So basically the W pump input equals to 1 minus Y times W pump 1 plus W pump 2, right? So now we have to determine what is the fraction of that steam. So that fraction of the steam Y equals to m6 divided by m5, right? So here m6 m6 fraction m5, right, the whole amount divided by the fraction of that vapor, okay. So now we know that basically for the pump is a steady flow device, we know that the expression for the pump, it's basically changing the pressure. So W pump 1, right, pump 1 expression would be specific heat times P2 minus P1, and W pump 2 would be V3 times P4 minus P3, right? So now we can see that from this this diagram, basically we know everything, we know all of those conditions, we know that pump input, heat input, turbine output, right? So we can determine basically the W net and Q in and the efficiency. So the W net would be, excuse me, W net would be that W turbine output minus W pump input, right? And efficiency expression, we know that W net divided by Q in, right? So we know everything about all of those parameters. So that's the expression, or that's the analysis of the open feed water system, right? However, open feed water system, it is still there are some challenge about the vapor mixing or liquid vapor mixing, or the quality control of the steam. So that's why people came up with another idea, which is the closed feed water system, right? So the closed feed water system is right here. You can see that when the turbine outlet is coming here, right, relatively high pressure compared to the 0.8, high pressure and high temperature is coming here, then what is happening, it's mixing, it's passing through a closed feed water heater. That meaning that the water and vapor, they're not mixing together, rather they are separate, they're passing through a duct, right? And then once it's increasing the temperature, that liquid, this is basically 2 to 3, that liquid is increasing the temperature, then that vapor, basically that vapor and this liquid again mixing in the mixing chamber, right? Mixing is happening in a separate chamber. However, in the closed feed water heater, mixing is not happening, mixing is happening in different place, okay, which is the mixing chamber. So that's the difference between the open feed water heating system and closed feed water heating system, okay. So in this particular case, we have already the TS diagram, which is basically, we have two pump. So pump 1 to 2, it's, we can see right here, increasing the pressure, right? And from there 2 to 4, basically we can see that actually it would be from 2 to 3, right? 2 to 3, we can see that it is happening 2 to 3 right here. And then from there 2 to, actually this water liquid is flowing through this duct, right? So that duct is basically gaining some temperature as well. The working fluid within the duct is getting from temperature, so it's going from 2 to 9. So 2 to 9, we can see that it's increasing the temperature. Okay, and then from 9 to 5, it's also increasing the temperature, mixing chamber we can see here. And from basically in the other pump, what is happening from 3 to saturated liquid to, it's increasing the pressure. So 3 to 4, we can see that again it's increasing the pressure. And then from 4 to 5 or 5 to 6, right, it's basically increasing the temperature of that cycle. Excuse me, basically increasing the temperature of the cycle to the maximum temperature. Again, we are taking two output, right, in the turbine. Basically, if it is 1 kilogram of vapor, then y gram or y kilogram of coming through this way, and 1 minus y kilogram of coming through this way. So this one will be y3, y, and this will be 1 minus y condenser, right? So for this case, let's take a look what is the turbine input and what is the turbine output, right? So in the closed feed water system, basically it is very similar to the closed feed water system. It is very similar to the what it's called, very similar to the open feed water system. So in this case, the Q in, it's happening basically in two places. One is that this boiler or the Q primary, and then another Q in is happening here, basically from 2 to 9. It's increasing the temperature, or the closed feed water system, feed water heater, right? And then Q out, simply it's happening in one place, which is the condenser, right? Q rejection at condenser, right? And then turbine work is simply here happening here, H6 minus H7, H6 minus H7, which is equals plus H8 minus H7, right? Excuse me, H7. Right, and then again we have two pump, right? So it will be pump 1 plus pump 2. So let me ask you one question here. So here the TS diagram is given, but if you look at your book, which is the diagram basically 10.17, diagram 10.17 and 10.18, you will see that more modification in the this feed water system. So I would like to ask you guys for the homework, basically for 10.17 and 10.18, to take a look or practice yourself how to draw the TS diagram from this type of modified Rankine cycle, right? Either it's reheating or either it's regeneration, and then draw the TS diagram and basically try to analyze the cycle. So that's all about today's class. We talked about the modified Rankine cycle, basically that how we can increase the cycle temperature, right, using a reheater, and we also talked about the regenerative. So we'll come back with the math video based on this topic. Thanks for watching this video, and we'll come back with math problem.